The NASA-funded ATLAS survey, it was discovered using their telescope at Rio Hurtado in Chile, and it was first detected as a speck of light moving relative to background stars.
In the past decade, humanity has glimpsed not one or two, but three messengers from beyond our solar system. In 2017, one ʻOumuamua raced through our skies. Just 2 years later, two Borisov appeared. Now, in 2025, astronomers have announced the discovery of three ATLAS, the third confirmed interstellar object, and one already proving to be unlike anything seen before. Rumors are that Quantum Eye ran a simulation on three ATLAS, and it's horrifying. Today, we'll unveil the whole truth. Let's get started. Discovery and classification. On the 1st of July 2025, astronomers operating the Asteroid Terrestrial Impact Last Alert System, or ATLAS survey telescope in Chile, confirmed the discovery of three ATLAS, the third known interstellar object to pass through our solar system. The find quickly drew international attention because interstellar visitors are extraordinarily rare, with only two others, one ʻOumuamua in 2017 and two Borisov in 2019, having ever been identified. Follow-up observations from multiple observatories confirmed that 3I Atlas was not gravitationally bound to the Sun. Its orbit is hyperbolic, with an eccentricity greater than 1, meaning it entered the solar system from interstellar space and will eventually depart, never to return. 3I Atlas may be among the oldest comet-like objects ever observed. The estimated age exceeds 7 billion years. This places its origin in the early days of the Milky Way, possibly in the thick disk population of stars that formed long before our Sun. If confirmed, this would mean that 3I Atlas has been wandering through interstellar space for a time span longer than the solar system itself has existed. Such an ancient body holds particular interest for planetary scientists because it could preserve chemical signatures from the galaxy's formative era, including volatile ices and dust grains that predate the Sun's birth by billions of years. Artificial intelligence holds significant promise in enhancing the detection and classification of interstellar objects like 3I ATLAS. Machine learning pipelines integrated into sky surveys, such as ATLAS, Pan-STARRS in Hawaii, and the upcoming Vera C. Rubin Observatory in Chile, could dramatically increase the efficiency of spotting faint, fast-moving bodies against crowded starfields. By training algorithms on archival data of comets, asteroids, and noise, researchers can reduce false positives and accelerate alerts for genuinely unusual trajectories. Once detected, AI-driven orbital analysis can rapidly distinguish whether an object's motion is consistent with solar system dynamics or points to an interstellar origin. But what do we know so far? Physical and chemical characteristics. Unlike most solar system comets, which are dominated by water ice, with smaller contributions from carbon monoxide and carbon dioxide, 3I Atlas has shown an unusually high abundance of carbon dioxide. Observations conducted using the James Webb Space Telescope revealed that the coma surrounding its nucleus is strongly carbon dioxide rich, with a carbon dioxide to water ratio of approximately 8:1. This ratio is far higher than that measured in typical solar system comets, which usually show carbon dioxide to water ratios closer to 1 to 10 or 5. Such a composition suggests that 3I Atlas may have formed in a region of its home system where carbon dioxide was more abundant or better preserved, pointing to different conditions of planetary system formation compared to our own. Ground-based optical and near-infrared imaging provided further insights into the comet's activity as it approached the inner solar system. The Gemini North Telescope in Hawaii and Gemini South in Chile both captured the rapid growth of a visible tail in August 2025, only weeks after its discovery. This active tail development was particularly notable because it began while the object was still more than 3 astronomical units from the Sun, a distance at which many solar system comets remain largely inactive. The brightening and tail formation demonstrated that volatile substances within the nucleus were sublimating quickly, releasing gas and dust into space. The The morphology of the tail, elongated and dynamically structured, indicated that the activity was not uniform but driven by localized jets. These jets likely originated from fractures or exposed volatile-rich patches on the nucleus, consistent with the idea that the surface of 3I Atlas has been reshaped by its eons-long exposure to cosmic rays and interstellar space. Complementary ultraviolet observations came from NASA's Neil Gehrels Swift Observatory. Its instruments detected strong hydroxyl emission in the ultraviolet spectrum. This is a well-established proxy for water sublimation. The hydroxyl radical is produced when ultraviolet sunlight photodissociates water molecules released from the nucleus. By measuring the intensity of this emission in August 2025, scientists estimated that 3I Atlas was releasing water at a rate of approximately 1.35 times 10 to the power of 27 molecules per second, equivalent to nearly 40 kilograms of water per second. This level of outgassing was measured when the comet was still about 3.5 astronomical units from the Sun. Compared to 2D Borisov, which also exhibited strong water release, 3I Atlas appears to be even more active. The James Webb Space Telescope contributed critical spectroscopic data that enabled precise characterization of the coma's chemical composition. Observations conducted with its near-infrared spectrograph, or NIRS-PEC, and mid-infrared instrument, or MIRI, confirmed the dominance of carbon dioxide and placed tight constraints on the relative abundances of water and other volatiles. This finding was corroborated by the Spectrophotometer for the History of the Universe, Epoch of Rhionization and ICE's Explorer, or SPHEREX. A NASA space telescope launched in 2025 to conduct a spectral all-sky survey. SPHEREX detected strong infrared absorption bands attributable to carbon dioxide and water ice in the coma of 3I Atlas. Clearly, the interstellar visitor has experienced significant thermal processing but managed to retain volatile-rich layers beneath its surface. Its high carbon dioxide content could reflect the environment of its formation, perhaps in a cold outer disk region where carbon dioxide ice condensed more efficiently than water ice. Alternatively, it may indicate that the comet underwent evolutionary changes during its billions of years in interstellar space, with cosmic rays selectively depleting water and leaving carbon dioxide-rich material more intact. Laboratory simulations of interstellar ice chemistry suggest that irradiation can indeed alter the abundance of volatiles in complex ways. The observed dust and gas dynamics also provide insights into the structure of the nucleus. The asymmetric tail development and the variability of gas emission suggest that 3IATLAS's nucleus is not homogeneous, but rather contains localized volatile-rich regions embedded within more refractory material. This heterogeneity is consistent with studies of solar system comets like 67P Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission between 2014 and 2016. In both cases, surface activity appears to be concentrated in specific areas. This means that the cometary nuclei are complex aggregates, not uniform icy spheres. However, the carbon dioxide-dominated nature of 3IATLAS sets it apart as chemically distinct. AI-based spectral analysis can dramatically reduce the time required to interpret the vast volumes of data generated by instruments like JWST, SPHEREX, and SWIFT. Machine learning algorithms can be trained to automatically classify spectral features, quickly identifying the presence of volatiles such as water, carbon dioxide, carbon monoxide, or more exotic compounds. Neural networks trained on large datasets of cometary spectra from both ground and space-based telescopes could also be used to flag anomalies in real time. As surveys like the Vera C. Rubin Observatory in Chile come online with its Legacy Survey of Space and Time, or LSST, the volume of cometary detections will increase dramatically. Automated anomaly detection powered by AI will ensure that interstellar candidates with unusual chemical or dynamical signatures are quickly escalated for detailed follow-up observations. For 3I Atlas, This means that its unique carbon dioxide-rich nature might have been identified even earlier, improving the coordination of global observing campaigns. Beyond classification, AI can play a role in modeling the physical processes driving cometary activity. Dust and gas dynamics in cometary cometae are governed by complex, non-linear interactions that are difficult to simulate with traditional computational models. Experimental approaches combining AI with emerging quantum computing architectures may allow researchers to run higher-fidelity simulations of sublimation, jet formation, and dust-gas interactions at scales and speeds previously unattainable. This could provide more accurate predictions of how the tail of an object like 3IATLAS will evolve as it approaches perihelion, which for this comet will occur on the 29th or 30th of October 2025 at a distance of 1.4 astronomical units from the Sun. Orbital path and observation timeline. Once initial observations were collected and refined, it became clear that 3IATLAS was following a hyperbolic trajectory with an eccentricity greater than 1, confirming its interstellar origin. While comets native to the solar system orbit the Sun along elliptical paths, interstellar objects like 3IATLAS are destined to pass through only once before continuing their journey into the galaxy. The object will continue outbound on its hyperbolic path, making its closest approach to Earth in mid-December 2025. At that time, the distance between 3I Atlas and our planet is projected to range between 170 and 270 million kilometers. Rest assured, this is far too distant to present any impact hazard. The comet's proximity to Earth will provide a valuable observation window when its coma and tail are expected to be well developed and accessible to a wide array of instruments. Both professional and amateur astronomers will likely track it, with larger facilities such as the European Southern Observatory's Very Large Telescope, or VLT, in Chile, the Keck Observatory in Hawaii, and the Subaru Telescope on Mauna Kea playing key roles in characterizing its physical state. Despite the interest generated by its approach, 3IATLAS will not linger in the solar system. Like ʻOumuamua and Borisov before it, the comet will escape the gravitational influence of the Sun and return to interstellar space. Once it crosses beyond the heliosphere in the coming decades, it will resume its journey through the Milky Way. Current orbital models indicate that it likely originated in the galactic thick disk, a stellar population composed of stars and planetary remnants that formed more than 7 billion years ago. Its velocity relative to the Sun, combined with its trajectory, suggests that it entered our solar system from the direction of the constellation Hercules and will depart toward the constellation Centaurus. The non-gravitational forces acting on 3IATLAS complicate efforts to predict its exact trajectory. Comets are subject not only to the gravitational pull of the Sun and planets, but also to the reactive forces produced by outgassing. As jets of gas and dust erupt from the nucleus, they impart tiny but measurable changes in velocity, which over time can shift the orbital path by significant amount. In the case of ʻOumuamua, such non-gravitational acceleration was observed, sparking debate about whether it was due to natural cometary activity or something more exotic. For 3I Atlas, the unusually high levels of carbon dioxide detected in its coma, combined with the water outgassing confirmed by SWIFT, make it likely that outgassing will play a substantial role in its trajectory near perihelion. Artificial intelligence offers a suite of tools that can enhance the accuracy of trajectory modeling under these complex conditions. AI-driven prediction models can incorporate the stochastic effects of outgassing, using real-time observational data to recalibrate orbital paths. By learning from the behavior of known solar system comets, such models can better anticipate how volatile release will alter the path of an interstellar body. Neural networks trained on decades of cometary orbital data could, for example, adjust trajectory estimates more quickly than traditional methods, providing astronomers with continuously updated forecasts during the weeks around perihelion and Earth's closest approach. Another area where AI applications hold value is in collision risk assessments. AI-assisted trajectory design could be used to generate potential flight paths for fast interceptors or flyby probes. A precedent for this exists in the European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, which is designed to wait in space until a suitable target is identified. AI algorithms could accelerate the process of identifying intercept windows, optimizing trajectories, and modeling spacecraft dynamics. But wait, there's more. Clash of theories. When 3I Atlas was confirmed as the third interstellar object on July 1, 2025, it immediately became the center of scientific debate, not only because of its trajectory, but also due to its unusual physical and chemical properties. Observations with the James Webb Space Telescope revealed that the carbon dioxide to water ratio in 3 IATLAS's emissions is highly unusual, roughly 8:1. Most solar system comets are dominated by water ice, with carbon dioxide playing a secondary role, typically in ratios closer to 1:1 or lower. Planetary scientists argue that this extreme enrichment of carbon dioxide may be the result of billions of years of interstellar exposure, during which water ices were preferentially stripped away by cosmic rays and ultraviolet radiation, while carbon dioxide-rich layers remained protected beneath. Such an explanation would also be consistent with models suggesting the comet's age is close to 7 billion years, predating the solar system itself. A second natural factor involves the object's motion. Like its predecessors, 1I ʻOumuamua and 2I Borisov, 3I Atlas exhibits non-gravitational accelerations that cannot be explained purely by Newtonian orbital dynamic. Data from Gemini North in Hawaii and the Swift Observatory in low Earth orbit have already detected jets of gas and dust venting from the surface, including strong OH emissions that indicate water breakdown. Such jetting can create small but measurable shifts in the comet's trajectory. Astronomers emphasize that these shifts, while puzzling, can be explained by asymmetric outgassing, similar to what has been observed in comets within our solar system, such as Comet 67P Churyumov-Gerasimenko, studied by ESA's Rosetta mission from 2014 to 2016. Despite the plausibility of natural explanations, Avi Loeb has consistently argued since the 2017 ʻOumuamua debates that extraordinary anomalies demand an open-minded scientific approach. Loeb, who holds the position of Frank B. Baird Jr. Professor of Science at Harvard University, quickly became one of the most visible figures in the global discussion over interstellar visitors. He was among the first to propose that ʻOumuamua's unprecedented characteristics, including its highly elongated, flat shape, its lack of a visible cometary tail, and its unexplained non-gravitational acceleration, might indicate something other than a naturally occurring object. In his 2021 book, Extraterrestrial, Loeb advanced the controversial hypothesis that ʻOumuamua could be a piece of alien technology, perhaps a light sail propelled by stellar radiation pressure. With the discovery of 3 IATLAS, Loeb has renewed these arguments, emphasizing that the scientific community must not dismiss the possibility of an engineered probe without first rigorously testing the evidence. In public lectures, interviews, and papers, he has highlighted several aspects of 3 IATLAS that, in his view, merit careful scrutiny: the unusual dominance of carbon dioxide in its coma, the wide range of size estimate from 320 meters to 5.6 kilometers, which complicates physical modeling, and the object's unusual jetting activity, which produces trajectory shifts not fully consistent with standard cometary outgassing models. To Loeb, these anomalies provide sufficient justification to conduct targeted searches for technosignatures, such as narrowband radio emissions detectable by facilities like the Allen Telescope Array in California, infrared heat signatures identifiable by the James Webb Space Telescope, or geometric surface features that might indicate artificial structuring. Loeb's stance represents a direct challenge to what he perceives as excessive scientific conservatism. After ʻOumuamua's appearance in 2017, many astronomers criticized his claims, yet Loeb has maintained that the real danger lies in the opposite extreme: dismissing anomalous data prematurely out of fear of professional ridicule or of being associated with fringe theories. He warns that such reluctance could blind science to genuinely revolutionary discoveries. Many in astrobiology and SETE, or Search for Extraterrestrial Intelligence, agree. At conferences such as the International Astronomical Union meetings, researchers have been split between those favoring cautious natural models and those supporting frameworks that do not exclude artificial possibilities. Artificial intelligence is already proving to be a key tool in navigating these competing interpretations. AI-driven signal detection systems are being applied to data streams from observatories, such as the Very Large Array in New Mexico and the Allen Telescope Array in California, searching for techno-signatures in radio and optical spectra. These machine learning tools can scan petabytes of data for narrowband or repeating signals far more efficiently than manual searches. Neural networks trained on known cometary spectra are also being used to identify outliers or spectral features that do not match typical cometary behavior, which could warrant closer scrutiny. AI applications extend to dynamics as well. By training algorithms on known comet trajectories, scientists can identify patterns in 3 IATLAS's motion that deviate from natural models. These deviations may simply highlight outgassing physics not yet fully understood, or they could point to engineered propulsion. Either way, AI-assisted comparative studies that analyze data from all 3 interstellar objects, ʻOumuamua, Borisov, and Atlas, are helping researchers quantify how unusual 3 IATLAS truly is relative to the population. Looking forward, the field is also eyeing the potential of quantum computing. While still in its experimental stages, quantum simulation could allow scientists to model volatile interactions at the quantum chemistry level, providing more accurate predictions of how exotic ices behave under interstellar exposure. This might resolve why carbon dioxide appears so dominant in 3 IATLAS. In parallel, hybrid AI quantum systems may eventually handle the astronomical big data problem. Billions of nightly detections from surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time will demand unprecedented computational power. Rare data can drive profound disagreements about interpretation. There are natural explanations grounded in established cometary physics and chemistry. Then, there is the insistence that science must be open to extraordinary possibilities. Artificial intelligence and, eventually, quantum computing promise to mediate this clash. By late 2025, when the object makes its closest approaches, the world will have a clearer picture of whether 3I Atlas is simply an ancient, carbon dioxide-rich wanderer from the galaxy's past, or whether it hints at something far more profound. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new upload. Also, don't miss this video you see on your screen right now. It's truly unbelievable.